Yeah, thank you so much, Dr. Rajesh, and really nice to be on this podium and talk about peer review. So I'll quickly share my screen, and some of you who have attended some of my sessions before know that it's relatively power packed and pretty fast. So I hope all of you will be focused on what we are going to discuss, and trust me, it's going to be pretty fast, and it's almost like a whirlwind. So if you lose touch, you're going to actually lose it. So try and be with me as far as you can, and let's dive deep a little bit into peer review. I'll share a little bit about my insights of how I do it, and there are multiple ways of doing the same thing, and our esteemed panelists will share with us what they do. But then there is a method to this madness, and let's hope that I'll be able to distill some of my learnings over the last decade or so in this next 1 hour. Yeah, so hopefully all of you have turned off your microphones, and feel free to type your questions in the chat box, and we'll get to them at the end during the Q&A session, and not interrupt with the ongoing presentation. Dr. Rajesh has already introduced me. So a quick correction is I was the associate editor of the Indian Journal of Ophthalmology, not the editor. Hopefully one day. And I have been an author, of course, and then I have been a reviewer of more than a decade, and I've been now on the associate editor of the IGO. So I've been on the editorial boards of multiple journals. So hopefully I'll be able to give you a unique perspective on with wearing all of these different hats as to what you should know as an author, as a reviewer, and then as an editor of a journal. So this is quite a proud moment, because when Dr. Santosh Honavar took over the editorial board of the Indian Journal of Ophthalmology, the impact factor was relatively low, and then he with his team, and I was one of the integral parts of the team, we were able to boost the impact factor of the journal to as high as 3.2, which was in 2022. So it's still pretty healthy now at about 2.2 or 2.3. So I think the good work is still continuing. So how did we get there? How did we bump up that impact factor? This is a huge jump in impact factor, almost 5 times, at least 4 times of what it was at baseline. So I think one of the very important cornerstones that we identified was peer review, and that it has to be precise, it has to be concise, it has to be rapid, as in you can't take like 3 months, 6 months, and the turnover time has to be good. So the quality of the review has to be as good as any out there, right? So what we decided to do was actually do a reviewer boot camp. That means a very power packed session for about a couple of hours, and we invited particular reviewers in different parts of the country, and we did about 3 or 4, I think about 4 or 5 boot camps over the first year of the editorship, and that boot camp helped us. And what I'm going to present to you is what we talked about way back in 2017, and I have modified that a little bit over the different learnings, and I have written about this in one of the issues of this was the May 2023 issue, and this is there online, and if there are any editors listening to this, you can actually look at this and look at the recipe to growing a journal, and I have shared my experiences, pretty much all of it, in this editorial. So what is peer review? So a lot of you might be uninitiated and thinking about listening to this, and the real idea is to look at a paper before it is published. Most of us will read papers after it is published, but then a select few will actually get to look at papers before they are published. So that's what we are talking about, before a paper is published. So who is a reviewer? Or he or she is regarded as an expert in the field. So the author, they are well published authors themselves. They are speaking at different meetings that you are attending, the BOA, the MOSCON, and the VRSI, the CARACON, and all of these. So most people who are on stage presenting are actually reviewers at the back end of papers that you might be submitting to journals, and they are actually called KOLs, or key opinion leaders. And trust me, if you are a KOL, you will be getting different invitations to review articles. The person who is going to review the paper should not have participated in the research directly, or its analysis, or in its writing in any form or manner. They are capable of providing suggestions to authors on how to improve the quality of their manuscript, right? So the main idea of a reviewer is to actually help the authors improve or bump up the quality of their paper. So the paper that is actually submitted, or rather the paper which is published, is far better in quality than what was submitted, and therefore has better readability, better citations, and therefore it helps the journal overall in the long run, right? And the reviewer should be capable of identifying any errors that need correcting before publication, right? So it's not good to actually look at papers and find faults in them, because it not only shows the author's oversight, but also the reviewer's oversight, and that happens and not infrequently. Right, so overall this is the process where you submit the paper, it goes to an editorial review, then it goes to peer review, where the editor sees, then the peer reviewer sees, it goes through this cycle of revisions, and then a decision is reached. So this is just an overview. So to give you a more detailed overview, the author submits a paper. Suppose you are an author, you submit a paper, it is taken, the first look is by the editor, that's called the editorial pre-review. The paper could straight away be rejected, and the author is notified of that, or the editor might think it's good enough and it assigned to reviewers. Reviewer will take its time, and then they will review and suggest a decision, which is then submitted to the editor and then to the author. It's either accept, revision, or reject. If it's a revision, then it is submitted back to the author, who revise and then resubmit it, and then editor checks the revisions, the reviewer also checks the revisions, and again this cycle continues till the paper is either rejected or accepted. If it's revision, then acceptance is not it's possible. Once accepted, proofs are generated, authors check the proofs, and it goes back to the publisher, right? So overall this is in a nutshell what peer review means. So if you see, the three main players are the author, the editor, and the reviewer. And if you see, the bulk of the work is done by the editor, right, who is looking at the paper before it is sent to peer review, and also after the reviewer, and seeing what the reviewer is seeing, and then communicating with the author, and then again to the reviewer, and back and forth, and then also to the publisher. So the editor plays a central role, of course, as we know, and however, the reviewer is vital in terms of improving the quality of the editor. Is not actually improving the quality of the paper, it's the reviewer who is improving the quality of the paper, right? So how well a journal is performing really depends on the reviewer and not only the editor, right? So, and that's something that all of us should know. There is a fourth person in all of this who is at the back end, and that's the publishing house. You can see it's blinking right now on your face, and it's very important to understand the roles of this publishing house, and what they do, right? So essentially, what the publishing house, just give me a second, right? So basically, publishing house is dealing with all the costs that are involved in a journal, right? There are some fixed costs and there are some flexible costs, but let's look at, a lot of people say, oh, this is expensive and why should I pay to read a paper, etc. So from a publishing house, if you look at it, they have multiple expenses, and I have listed 12, and there are plenty more, but so online platform, there is a website maintenance, salaried staff, they have printing, which is quite a huge expense, at least when we were at the IGO. So IGO used to publish like 20,000 copies every month. That's like huge, right? So each copy used to be voluminous, like 600 pages, and you're printing 20,000 such. That's like that really bumps up costs. There are plagiarism checkers and so many other things. English language editing, indexing rights, like PubMed and all of these. Actually, you have to pay recurring fees to these these indexing agencies to keep your journal indexed in that, right? So that also has its costs. So there are definite costs. So who pays for this, right? It's important to understand as authors is that either the reader pays for it, right? That's called the subscription based model. So the reader is paying for for all of this cost, or it could be flipped, the author pays for this. It's called the open access model, where the author is actually charged. So you are actually charged, and then the reader actually gets it all for free, right? So that is the other model, that's called open access. And third is neither pays for it, right? So then somebody has to pay for it, right? So there is an intermediary somewhere, like the AIOS. In the case of IGO, neither the author is paying nor the reader is paying, right? That is perhaps the best model, isn't it? So authors are not burdened, neither is the reader, but then the charges are being borne by the society which is actually running the journal, right? So for the Maharashtra Ophthalmological Society pays for the JCOR, right? So then it is free for the author as well as for the readership, right? So it's important that we try and isolate some of these journals and bump up their quality, so that we get to publish as authors, as well as people get to read it widespread, and nobody really has to pay in this process. There are very few such journals, right? And IGO is one of them. JCOR is also one of them, right? So remember that everything is working on this revenue model, isn't it? So either one of the three, and the publisher is really working for revenue, isn't it? So I mean, this is a basic that all of us should understand. Also remember that the author is writing a paper and submitting it. The reviewer is also looking at that same paper, but the perspectives are entirely different. Why? That's because the author is in love with their own work and they are only looking at the positives, while the reviewer has only one job, and that is mainly to find problems in the paper and tell the author, to improve that paper, right? So the same paper is being looked at with very different angles right from the beginning. So the author and the reviewer are looking at the same paper but at entirely different angle and perspective. So let's quickly look at some of these perspectives from a historical point of view. So I have identified some, and you will get an idea of what we're talking about. So this is a paper which was published in none other than the Lancet, right? That is the one of the biggest journals in all of medicine, right? And if you see this paper, it talks about hydroxychloroquine or chloroquine with or without a macrolide for treatment of COVID-19, a multinational registry analysis, right? And if you see, this is written by Mandeep Mehra, Sapan Desai, Amit Patel, and so entire paper was found to be fake later on, right? So it was done with a fake registry. There was no multinational registry at all. Everything was helter-skelter. This was during COVID times, and people were talking about HCQ, if you remember, all the time. Even people like Donald Trump came out and said, "Oh, I take HCQ, and so should you." But then these papers were found to be fake, entirely fake. However, this paper was reviewed by somebody, isn't it? We don't know who that is, but the reviewer clearly did not find any problems. If you see, this is from 96,000 patients, and they're talking about these from like 90 countries or something like that, right? So this was published and then retracted. This is another paper which was published in the New England Journal of Medicine, which is an even better journal, if not, right? So it talks about cardiovascular disease, drug therapy and mortality in COVID-19. See, the authors are the same: Mandeep Mehra, Sapan Desai, Amit Patel. And this article was also retracted from the New England Journal of Medicine, right? So if such large journals can actually miss papers, who are you and me, right? We can definitely miss papers. We are all humans. But what we're going to learn now is how we should not miss any of this. I think it's really important that reviewers do their job so that things like this do not arise. So I've written an editorial on this, on my perspectives on so what we can learn from these retracted papers, and this was actually quite a bit read at the time. Now the other flip side is, let's look at good papers which did not make it. So this was the first paper on the citric acid cycle. This is by Hans Krebs. We know about the Krebs cycle, and this was the paper which got him the Nobel Prize. And the first journal that he thought about submitting it was their main journal, that's the Journal of Biochemistry. But that paper was rejected. Why it was rejected is because the reviewers did not find much in what they were doing. That went on to win a Nobel Prize. So it was submitted in a very obscure journal at the time in the 1930s, and that journal is called Enzymologica, and now it is a very large journal. And to boot rejection, the people wrote a criticism which was actually published in the Journal of Biochemistry. So this is the citric acid cycle, and this is criticism, and this is a screenshot showing a reply of the criticism by Hans Adolf Krebs, and people who have written the criticism's name is also here. Imagine rejecting the original paper and then writing a criticism on this paper, and that criticism is published in the main journal, but it was not, the actual paper was published in an obscure journal. So why is, again, peer reviewers were responsible for that early rejection, right? So they could not tolerate it, and then they actually have written, tried to demean the paper as well. But then remember, this went on to win the Nobel Prize. Another example from ophthalmology, and this is about fundus fluorescein angiography. So this talks about a method of photographing fluorescence in circulating blood in the human retina, right? This was the first paper by Novotny and Alves about FFA. This was in the 1960s, and this is a link to the original article which was published in the journal Circulation, and not in Ophthalmology or JAMA Ophthalmology, or that time it was Archives, or any of these RO or any of these big journals. Right, so reviewers again definitely rejected this paper, which went on to define how retina practice has been done even today. Right, so bad papers and good papers are in their own place. Bad papers can get accepted, good papers can get rejected, like I've already shown you. So the fine line there is, or the the person who is really responsible for a lot of this, either blame or not, is the peer reviewer. So it's really important for us to understand how to do a proper peer review. Remember, we are looking at something which is pre-published, it's not yet published, right? Remember, 90% of papers which are submitted are going to get rejected. So a lot of the common ophthalmologist or the common person is not going to be able to read what a peer reviewer reads. but also the skills that we need to assess a published paper are very similar to this, right? So what we are going to look in the next suppose about half an hour or so is, how do you review a paper which is before publication and use the same skills to identify good papers which are already published, and sieve them out from the bad papers and use all of that information to your own advantage in your own clinics, right? So all of these skills will overlap a little bit of over the next half an hour. So a quick my experience of the 15 years, this is one topic which I have reviewed multiple times. So this paper is published in 2011. It talks about the incidence and long-term outcomes of toxic anterior segment syndrome at Arvind Eye Hospital. You see, this was published in 2011 in Journal of Cataract Refractive Surgery. And I have reviewed more than 50 papers on this one topic over the next 10 years. So that's about 2021, 2022. And believe me, a lot of my colleagues a lot of my co-authors have also reviewed a lot of these papers. So imagine the influence this group has had on how the literature has evolved on toxic anterior segment syndrome, right? So it's a very large influence a reviewer can have on how a literature of a particular pathology is actually evolving over time, isn't it? It's another paper which I have reviewed for the journal Retina, and there are plenty of RCTs that I have reviewed, but this is one which has really influenced how we treat AMD now. It talks about efficacy and safety of intravitreal aflibercept using a treat and extend regimen. Those of you in retina practice would have heard about this term, treat and extend. So what we do is we give an injection and then we call the patient about 2 weeks later than what they would otherwise come, and then we re-inject irrespective of whether the disease is there or not. We then call the patient 4 weeks later, then 6 weeks later, then 8 weeks later. So what we're trying to do is extend the gap between injections, because the disease is just going to come relentlessly again and again if you give too much of a gap, right? So this is the study which actually defined the term treat and extend. So there are two studies, one is ARIES and the other is Altair. So I happened to review the ARIES study, and this was published by the Australian group led by Paul Mitchell. And so if I were to show you all the comments that I gave, that ranged for almost 4 pages, and a lot of changes were made in that paper and the way it was analyzed, results presented. So what I'm trying to show you is that a reviewer can have a humongous influence on how people practice medicine going forwards, if you're doing it right. If you have done a good job over the period of a decade or so, you are going to then attract attention of some of the top journals. You might then start reviewing RCTs, like I said I have done. And so it's not just me, but a lot of people in India are now exerting their influences on how medicine is evolving, isn't it? So if I say, or if a group of reviewers say, oh, this AI does not detect diabetic retinopathy enough, that paper may not get published in the top journal, and therefore the world may not even see that AI, isn't it? But then it may actually be a good AI, like I showed you. Some good papers may sometimes get rejected. So the responsibility is humongous, isn't it? So with immense power comes immense responsibility. So take that very seriously. But remember that every word that you write or review is going to have a huge exponential influence on medicine going forwards. Therefore, we need to do a good job. There are many negatives, people call it biased. Some of my biases may turn out into my reviews. People abuse this position, saying, that, oh, I'm doing something similar and I don't want the author to publish this paper before me. So you will actually, find faults and, sort of reject the paper and then get your own paper published. So that's like abuse. But then, that's jealousy, I would say, and that does happen, but it shouldn't. And a lot of people say, oh, it just delays publication. And nowadays, to overcome this, there are preprint servers, if you've heard about them. There is MedArchive, and there is there are a lot of others like preprints. They are called preprints, and what they do is they actually publish a paper without even peer review, and then people start reviewing the paper. So that clearly gives you a DOI number, that is a unique identification number, and then nobody can actually steal your work, right? So even if it's getting delayed in publishing in a journal, it will still be out there for people to read if it's that important. And remember that the first report of COVID-19, the first ever report from Wuhan in China, was actually published preprint. It got published as a letter to editor in January of 2020, but it was published in preprint almost 10 days before. So a lot of this is also happening. So why do you review? You want to stay up to date. As a reviewer, you will stay up to date, right? You will read on the latest developments, treatment options for a particular disease. It will help you critically appraise yourself, right? So your practice you will appraise your way of looking at literature, uh, and what are the problems, what are not, and then same skills, like I said, will help you as a clinician, isn't it, for troubleshooting, for getting hold of the good papers and discarding the bad ones, right? So if somebody were a good reviewer, they would never adopt flax straight away in the form it was maybe 5 years back, and that is femtosecond cataract. But now, of course, it's getting better, and I don't have anything against any procedure. But then 4 or 5 years back, most of these papers showed that flax wasn't up there. But then if somebody was a good reviewer, they would see it and they would not invest in flax right away. But then somebody who's not great at critical appraisal may not see some of those trends, right? It of course increases your knowledge, because to review you need to know a lot about that subject, right? So you will learn from fellow reviewers as well, and you will increase your knowledge about that particular disease. Look at it as academic service, so give back to your specialty. Also, you can teach students how to do this. It helps in professional growth. So the reviewers are now counted for career advancements in some of the top universities, and there is a website called PubLaunch, where you can have a reviewer account, and whatever you review will get credited into your PubLaunch account. So that's something that you can look at, and of course it helps you get to the KOL status, or the the key opinion leaders. So it's very important in your particular field. It gains a lot of peer respect as well, right? So there are a lot of these perks of doing good peer reviews, and I think most important is the influence that you might have on evolving literature. When you look back, might sometimes be immense. So quickly, this is how I thought we'll divide it. We'll look at the editor's perspective, then some broad guidelines on how to peer review, and then specifics on how to peer review, and if we have time, a quick live demo. So how are reviewers selected by an editor? As I told you, a reviewer is going to first and foremost be an expert in a particular field. So they would have published a lot in that particular field, and therefore they are considered to be experts in that particular field, right? So there are electronic systems such as database searches, which the review, the publisher provides. Sometimes there are nowadays there are AI driven matches, right? So that the AI picks up the abstract and then suggests reviewers based on the reviewer may or may not accept it, but then AI driven matches are also there. So that's how editors come to know that, oh, this is a paper which is well matched with this person, right? So it's based on their previous history of what they have published. Then there are scoring system based on previous reviews, and of course there are sometimes special reviewers like statistical reviewers, methodologists. There are people who are called methodologists. They just do and deal with methodology of a particular study or clinical trial. And then there are some even people who are called trial specialists. They're not that many, but then these can also serve as particular reviewers for a particular paper. Right? And who is not selected is if that person is found to have a conflict of interest in a particular, say, a product, or or is from the same institution. That's also like a conflict of interest. Who is of course a co-author himself or herself in that particular paper. How can they review the paper, right? There are some confidentiality issues, and there are competing interests. This basically in terms of you are consulting for a particular company, say a pharma company, and and you are reviewing a paper which is based on that drug from that company. And you want, because you're getting paid by that company, you want to show only the good aspects of that paper, and you want to reject a paper which shows the drug in bad light, right? So then if that is happening, that is something that should not happen, right? So all reviewers are asked to sign such documents which says that there are no confidentiality issues and I have no competing interests, right? And that sometimes better be true. So should you accept an invitation? Now this is from a reviewer's point of view. So the editor says, okay, this is a good match, will you review for me? So what you should first do is consider your own expertise. Are you expertised enough to review this paper? It may be simple paper or maybe a very complex paper, and this is a bit subjective. Let's say you are, and you feel that you are confident enough. Do you have enough time available to meet that deadline, say 6 weeks or whatever you have been given? Are you happy with the journal's peer review process? A lot of it is now online, but then the biggest thing is it masked? Are you, or is your name as a reviewer going to be revealed to the author? And that's called an open review system nowadays, right? So, and also when you're reviewing, is the author name masked to you? That's called a masked review. So like IGO has a masked review, so a lot of times you don't know, or most of the times you don't know who the author is, and the author doesn't know who the reviewer is, and most people are comfortable with that kind of an approach, right? But then as I'll show you a little going ahead, that your name may actually be out in the open. that you have reviewed this paper, and that is happening in open access journals with open review, that's called, right? So are you happy with all of that? Do you have any conflicts of interests? And this is very important for you to judge, right? Any financial or academic, personal, intellectual, or any kind of interest that you might have, which will not allow you to do a good job. And then the journal's reputation. Sometimes you say, oh, everything is fine, but this journal, I haven't heard about this and I'm not sure, and I think it's predatory and all of that. So then that might actually pull you back and say, oh, I don't want to review it at present, right? Because so some of these points you should think about before you accept a review from a particular journal. Some general guidelines are your language should be collegial and cordial. You can't just say, oh, this is rubbish, I don't want to accept this. Or some people write just 2 or 3 lines and say, oh, it's not good enough, reject. But then that's, I think, being that's being rash. So that can't be, right? Then comments to the editor and author should be separate, where you can be more expressive to the editor but not as much to the author, where you only are scientific and not, there are no emotions in your comments to the author, but you can actually vent out and tell the editor, how could you even send this for peer review, it's such a poor paper. And you can do that to the editor but not to the author. And sometimes, trust me, that does happen. You can prepare a broad comment, that is a single paragraph comprising of the study question, design and analysis, as well as positive and negatives. Let me show you an example. So say the author presents, so you can say the author, this is just the beginning of your review, the first sentence. You say the author's present an interesting study on, then you insert the study question, right? Using A, then you insert the design, RCT or whatever. There are certain inherent problems with, then you insert the problem. Say you say an analysis or whatever. Please see my specific comments on improving the quality of the manuscript, right? So these are also, revisions, right? So these are all specifics, but then the author can go ahead and look down, or you can just say that these drawbacks make the study too weak. Of course, you're giving the drawbacks, but right at the top, you're saying, the drawbacks make the study too weak to be considered, or make this paper untenable or cannot be considered further. Right, so right at the beginning, you give the author some information in terms of, so this is a quick summary or a executive summary, right? So, and if this shows a lot of clarity in the reviewer's mind and what they are doing, right? So this is the beginning of the review, and this makes your review impressive to the editor as well, right? Also, good review, remember, should be about 1 to 3 pages long. It should have 12 font, 2 spacing on Word document. It can't be, very crowded and with a very small font, which is very difficult to read. It should not take more than 3 hours of your valuable time. Say half an hour to 3 hours, and you will see as you review more, your time will start reducing, and you will say, oh, 15 minutes mein ho gaya ye. It's possible sometimes. And it should have separate comments for the title, the abstract, and the manuscript body, right? So if you feel problems with the title, highlighted, then concentrate on the abstract and tell the authors how they can improve their abstract. And trust me, this is the most poorly written part of the paper. So the reviewer's role in improving the abstract is very important. And then on the manuscript body, you tell them about problems with different sections, as we'll see some specifics, and you can tell them how to improve their tables, figures, legends, references, etc. And should use page and line numbers to draw author's attention. Say line 4 page or whatever, line 42 page 5, this is I don't agree with, or something like that. So that will draw their particular attention to that specific point that you're making, right? So these are broad guidelines, and I showed you the editorial perspective on how editors might choose and whether you should accept it or not. Some broad guidelines of being cordial and all of that, but we haven't gone to the specifics, right? So the real crux of the session is, how do I do this? How do I do a standout review? And remember, you have to do justice to the author, who has taken like a year, maybe year and a half, to go through, analyze, write. You have to do justice to the editor, who has actually picked you for that responsibility, right? And then you have to importantly do justice to the readership, right? Who are then going to read a paper and say, oh, this is very poor, how did it even get published? Or you'll say, oh, this is a fantastic paper, and it has helped me so much in my practice. So a lot of that responsibility lies with the reviewer, right? So how do you do a standout review is what we are actually going to see next in the next about 20 minutes or so. First and foremost, these are the questions that you need to ask. These are at least 3 different questions. First is, what is the study question? What is the study talking about? Can you define it well? And we'll see how to do that. Second is, what is the study design that has been used, and is it appropriate? Importantly, is it appropriate to answer this study question? right? That's the second first, and you will see that a lot of these studies will drop out right here, but 70-80% of your reviews will go out saying, oh, study question is I am not sure, right? And it's not well defined. And then the study design is pretty poor to answer this particular study question. Then you ask about statistics, is this okay or not? And I'll show you some very key statistics that most of us would miss, but then if you know it as a reviewer, then you know it as an author, and then you don't know it as a reader, right? And that will really help you adopt papers to your own practice. And then of course there are certain differences in reviewing randomized trials compared to some of the others, and also reviewing systematic reviews and meta-analysis are also slightly different. So I thought I'll dedicate a quick 3 or 4 slides and put it as a separate part, right? So let's look at how to define the study question. If you're an author, you use this. If you're a reviewer as well, you use this, right? So you use the PICOT approach to define the study question, where P stands for participants, which really means inclusion and exclusion. So when you're reading a paper, the method section, as a reviewer, you need to be crystal clear who were included and who were not, right? Then what was the intervention done, or what is the exposure here, right? Was a surgery done? Was a medicine given? Was an interview done? Or was a survey conducted, or whatever that may be, right? So what it really means is, how was the data collected? How was the data gathered? So that's the intervention part. The C stands for the comparison group, where does this study need a comparison group? Somebody says, oh, I have a new technique to improve things, or I have done say so and so procedure for so and so disease, or I have a new IOL which is better than existing one. So whatever that may be, how will I know it's better than what I'm doing today? If it's it's definitely better, then I'll tend to adopt that thing, isn't it? But if it's not, imagine a study which is doing femtosecond cataract surgery alone, not comparing it with phacoemulsification at all. So are you likely to even look at that paper? You might, but then are you still likely to change from phaco to flax based on that paper? Absolutely not, right? So that's a very obvious example, but then almost all studies will have these kind of examples. So try and identify, is there a comparison group? If not, would this study do well with a comparison group? Now we are looking at it from a reviewer's point of view, remember. Then what are the outcome measures? Are they defined well enough, right? And then what is the primary outcome? And we'll take some examples later in the statistics section. And lastly, what is the type of study? Is it a prospective versus retrospective? Was randomization done or not, etc., right? Let's take some examples. Say there is a study to treat uncontrolled diabetes, and you are reviewing that kind of study. Now let's look at what the PICO would stand for. So P should be uncontrolled diabetic means what? Define it well. What kind of patients were included? Adults, or we know IDDM can happen in kids as well. Duration of diabetes, recently diagnosed versus long-standing. So define them. Are there any comorbidities, etc., right? So when you read the P, you should be able to sort of picture that ideal study participant who will go into the study, right? So it's very important to have basics, or rather specifics, right? So who were included and who were excluded. I stands for intervention. So maybe hypoglycemic agents were used, or insulin was used, or something else. You want to show something is as good as, or something is better than, like that, right? So this is intervention. C stands for comparison group. So was standard of care for diabetes used at present, or both the groups are also new, right? Maybe one group is very new and one group is also relatively new. So what was being done there. And O is drop in blood glucose level, right? So that's an outcome measure. So it's measured as continuous, or you can say it is less than 140, and then it's good control, or you can say it's 50% reduction from baseline. Again, that's a yes no kind of a variable, isn't it? So that's how do you define it really makes every a lot of difference in how it is analyzed and data presented. So are the outcome measures defined well is what we are trying to look at, right? So ask whether all these study questions are novel enough to be considered, isn't it? So this is the PICO. Let's take an ophthalmic example of study to treat rapidly progressing myopia. Say so an ideal study would look like this, where the P stands for children between 6 and 12 years with rapidly progressive myopia, defined as more than 1 diopters per year. So these are just examples. Despite using best corrected spectacle correction regularly, currently under -2 refraction, with or without family history of high myopia, with or without ocular comorbidities. So whatever, you could say with or without. So you could say I am going to exclude those with high myopia family history because they are going to progress what may, come what may. Or you could just do a study on those who have a family history of high myopia, because that's where it really matters, right? So that's a P. I stands for, you might say the children are going to use DIMS glasses versus low dose atropine, and I want to show both are equal to each other, or I want to show one is better than the other. So that's sort of perspective comes in. C stands for standard of care for myopia at present. Is this being used? So if you consider nothing to be standard of care, then maybe no comparison group is okay, right? But then if you consider low dose atropine now as an established way, maybe DIMS classes are newer ones, then that's, comparison group should be there, right? So one of the two will be a comparison group, whichever is older, right, or established one. So that's, that's the way to think about it. And O is the outcome measure. So you want to talk about reduction in myopia progression at 2 years follow-up, right? So how do you define this? Reduction in myopia progression. So if you say, progression is more than 1 diopter per year in the beginning, then now your, the outcome should be how many kids did not progress to 1 diopter per year. So something like that. Or you could say mean progression minus 0.6, minus 0.7, minus 0.8, or whatever. So I'm going to compare between DIMS glasses and low dose atropine. What is the mean change in refraction? Now remember, that's going to be like a continuous variable. It could vary from minus 0.2, 0.3 to like minus 3, minus 4. Or you could also say how many actually progress more than 1 diopter still. Right? That's going to be a percentage or proportion. That's going to be different. So lastly, ask whether all of this is novel enough to be considered. You will realize that a lot of it is going to be missing in at least 50% of the papers that you review. Right? It's going to be just missing, and you don't know what is happening. So your sort of threshold to accept these kind of papers are going to be low. Let's look at the study design. There are main 2 types of designs. One is observational, where you don't do anything, you just observe. You're not intervening at all. The other are called experimental studies, where you are actually doing something, right? You're telling, you're controlling the administration of a particular test or drug or something like that. So typically these are randomized trials or randomized studies. These are experimental studies, and observational studies are the other ones. So what are observational studies? It starts from basics like case reports, case series, cross-sectional, case control, and cohort studies. These are all observational studies. So where do the terminologies of retrospective, prospective fit into all of this? So retrospective really means, as we know, looking back, right? So the disease has already happened, and then maybe another group who don't have disease, and you're going to look back. You're going to collect data from by looking back, and you're going to see how many were exposed to a particular risk and not exposed to a risk. So what you're really doing is comparing and analyzing differences in risk factors for a particular disease, right? So that's generally how retrospective studies are done, where outcome has already happened and the exposure to risk is what we're trying to study. So remember, you're reviewing a paper. Is this retrospective design okay to answer this study question? Remember, we have used the PICO approach to define the question. Now, do you think this retrospective study design is okay to study this, to answer the study question, is the question that you're going to ask. So case control studies are something like that, right? So case and control. Case means disease has already happened, and control means, so case control studies are generally examples of retrospective studies. It's good for examining rare or new diseases where you don't know much about it and you don't know whether I want to do something going forward. So you can look back. Studying diseases with long latent periods, testing a possible association between disease or a condition and multiple exposures. We don't know. So, a lot of the times you won't know whether the lung cancer is being caused by cigarette smoking or not. So a lot of retrospective studies were done to actually find whether cigarette smoking causes lung cancer, and then were confirmed with more prospective studies looking at databases, right? So that's how, say AMD, and you say smoking increases risk of AMD. How have these actually come about? Initially, they were looked at with retrospective designs, and then only in prospective designs with the ARED study and all of that, right? So case control studies are harbingers for prospective studies if there is enough in that, right? There are of course limitations. That it's difficult to examine rare exposures, do not provide evidence about multiple effects on by a single exposure. Say smoking will cause AMD, it will cause lung cancer, it will cause cardiovascular disease and a lot of other things. So that's something that you cannot study with this kind of a retrospective design. It is difficult to establish temporal relationships, particularly say a side effect of a particular drug. If it happens within an hour, it's most likely because of the drug. If it happens within a day, it is still likely. But if it happens after a week, it may be less and less likely. So temporal association or relationship means time. So with retrospective, as we know, we can't always tell, because so those case files may not actually may have dates, but may not tell us a lot more than that. So and also, of course, remember, it's always difficult to identify a good control group. You may say age match controls or something like that, but it's very difficult to find a control group in that. So these are looking back. So is this case control? So you will say, okay, this is a retrospective study, so means the case and control. Now let's see if there are controls, and you may say, oh, there are no controls at all in this. So say for example, I want to study something which is, like I said, rare. I will say caterpillar hair in the eye. And I'm going to look back and say, oh, I had these 15 patients of caterpillar hair, and I want to publish because nobody else has. So this is like a new disease, say, at the time. Now, how do I get a control group? So there are patients from 15 years to 70 years in my study group. So it's very difficult to get a control group in that kind of a design, right? So currently the study that is being published or is being submitted, does that study design help in answering the study question? Of course, prospective, as we know, you enroll based on all of them are non-disease subjects. They are at risk of disease, and you follow them up for a period of time, and then you see how many got disease and how many did not get disease, right? So you compare incidence over time and analyze differences. So exposure is there, outcome has not yet happened. We obviously know these things, right? So prospective, remember, so any study can really be done in a prospective or retrospective study. Prospective is better because you have a lot of control. You will know when the disease started, what caused this disease to start, is this causality, is this actually leading to this or not, based on temporal associations and all of that we have discussed, right? So prospective is generally better than retrospective. It's far more controlled, right? And outcomes you can study very clearly and get better data. But pretty much any study can be done in a prospective versus a retrospective study, right? So you can observe the incidence of the disease, study prognosis, natural history, and so many other things. I'll quickly go beyond. So the other is experimental studies or randomized trials. You randomly assign participants to groups, say drug A versus drug B, and this test intervention versus the comparison group, say a new glaucoma medicine versus an old glaucoma medication, or a new study, say MIGS or some of that, versus an established surgery like trabeculectomy, and then you see whether outcome, that is drop in intraocular pressure, happened or didn't happen. So no outcome versus outcome, and similarly in that. So this is basically a randomized trial design, right? So what we mean by that is, so there are, say, drug A and drug B, and all of these participants are randomly based on, say, a throw of a die or something into each of these drugs. But if a physician comes and tells, okay, you go into drug A, and then you go into drug B, again, next third patient, you go here and you go there, it's not okay, right? Because now what's the point of this? Not really randomization, isn't it? So there's a lot of bias, the physician's bias is coming into it. So randomization, what it really does is takes care of bias, right? So this is a quick summary of different kinds of study questions, and you can look at the recording and go over all of this again. So say incidence studies have to be prospective, isn't it? So cohort studies, prevalence studies can't be prospective, because you want to look at how many have disease at a particular time point. So you want to do cross-sectional studies. A therapy, say a new drug or a new medicine or a new intraocular lens, has the best way, these are the best ways of looking at it, is a randomized trial, right? So there are multiple ways of doing the same study, but which is the best design is something that you need to ascertain. Coming to let's look at, so what we have now looked at is how do you define a study, how do you understand whether the study design is appropriate for the study question or not. And in the larger scheme of things, we looked at broad guidelines, and then we are looking at specific guidelines. Quickly take a break. I'm going to have a quick sip of water, and then we can continue. I hope some of you are still here and are able to pick up what we are understanding.
Yes, definitely. We are enjoying.
We are all still here.
All right, sounds good.
We are not only enjoying but learning so many things. First time I am learning all these points.
That's great. Okay, so I'm back, and I hope it's great to see all of you still around and hanging around. So let's now look at statistics, which is quite a difficult topic for most of us, but trust me, it is not as difficult as you think it is. And I'm going to just you can have your maybe your calculator or maybe your phones out, and you can do these statistics with me, because as a reviewer you don't want to do massive scale statistics, right? And you can't do it because you don't have the Excel or the data. But what you can actually do is make 2x2 tables and understand what's happening. So let's look at statistics. So first and foremost, almost all statistics are based on outcome measures. Treatment, they are called treatment effects, right? So is the outcome a dichotomous, that is only two possibilities, or is it a continuous? IOP control hua ya nahi? You will say less than 18 good control, worse than 18 bad control. Or you can say mean drop in intraocular pressure, 2.3 millimeters mercury in one group and say 3.2 millimeters mercury reduction in the other group. So dichotomous will be in percentages, right? And continuous will be in with means and standard deviations. So quickly, what are continuous variables? They can take many different values. Remember, this is the outcome, right? Now all variables could either be continuous or categorical. So continuous means from lowest to highest, it will have a unit to it, and they'll be described as mean with standard deviation. And categorical means things, as it says, categories. So things are categorized into baskets, 2 baskets, 3 baskets, 4 baskets, whatever. And these are going to be in proportions or percentages. So how many percent people are in basket A? Say men and women. So basket A and basket B only. Say there are 3 groups of drugs, A, B and C. So you will say 30% got drug A, 40% got drug B, and the remaining 30% got drug C. So whenever looking at percentages, remember you are looking at categorical variables. A quick quick brush up is age will always be in years. It will be in mean and standard deviation. These are continuous variables. BCVA is in logmar. Macular thickness, pachymetry is in microns. Follow up is going to be in months or weeks or years. These are all continuous variables. Now look at categoricals. So gender is either male, female, or something other. Success could be yes, no. Types of trauma, as we know, is only blunt or open versus closed globe. Types of injections, say you have 3 or 4 different types in a particular study. Stages of diabetic retinopathy, again, these only can be mild, moderate, severe, NPDR, PDR, and say one more. So it's 5 or 6 baskets, but they are all in percentages, right? So these are categoricals. So when you have outcomes which are categorical, and we are comparing across groups, say drug A and drug B, how many percentage men in drug A versus percentage men in drug B? This is done using the chi-square test. Very simple. CAT is chi. Categorical across groups is chi-square test. And most authors won't make a mistake into this. And you can ask which test did you do. You can't actually go and cross check it, right? So this is something that you should know about, but you can't do anything about it. But these are something that you can calculate on your own. So let's look at these 4 and try and look at some of these in published papers, in some of the best papers, and trust me, you will be able to find these on your own in every paper that you read. So what is absolute risk difference? What is numbers to be treated, risk ratio and odds ratio? These are all sounding quite difficult to you at present, but trust me, it's not at all difficult. So let's look at what an event means. So that's an outcome which has happened, right? So say there is an experimental group and there is a comparison group. So remember, if there is no comparison group, there is only one group, then none of this is possible, just not possible. This is only when you're comparing one with the other, 1 with 2 or 1 with 3 or maybe even more. But when you're comparing one with none of this is possible, right? So a comparison group is really important for any study design. Whenever you're doing one or you're reviewing one, try and look at whether the comparison group is there. So event means hua, PC rent hua, or end up happened, or whatever that may be. So event and no event, and on this side it's experiment and comparison. So if the event we call it A and no event we call it B, the total of experimental patients are A plus B, right? And comparison is C, and comparison group mein people did not have an event, it is D, and we call it C plus D, right? So overall this is, now forget about everything else, event and no event in the experimental and comparison group. Now what does risk mean? Risk means how many had event out of the total. So in the experimental group, how many had event is A, and how many total were in the experimental group? A plus B, right? So so this is the risk formula, number of events upon number of participants in that group. So in the experimental group, risk for that event happening is A divided by A upon A plus B. Similarly, in the comparison group, it is just C upon C plus D, right? I mean, it's not at all difficult. It's really basic maths, like first, second standard students will be able to understand this, right? So A upon A plus B and C upon C plus D. Based on this, let's look at all of these others, right? So let's take an example. Say intensive therapy of diabetes versus conventional therapy for diabetes, and we are looking at the outcome as progression of diabetic retinopathy to PDR, say, right? So in the intensive group, out of 596, 36 had progression to PDR, right? So A upon A plus B. And in the conventional group, that is, you're not treating it that aggressively, out of 581 total patients, 122 had progression. Simple, right? So what is the risk of progression in intensive group? 36 upon 596. And in the conventional group, what is the risk of progression? 122 upon 581, right? Now so these are very basic. Now let's look at this absolute risk difference, which we don't use, by the way, but we should know. Absolute risk difference is the risk in one group minus the risk in the other group. So A upon A plus B minus C upon C plus D. So that's 36 divided by 596. So this is how it is. See, A upon A plus B minus C upon C plus D. That is 36 out of 596 minus 122 upon 581. Simple, right? A upon A plus B minus, we are now subtracting each because you're looking at difference. So that's, this numbers you can do on your own, but these are the right numbers. So 0.06 minus 0.21 is minus 0.15. This negative means low risk. So you will say, how do you interpret this is 15% lower risk of progression with intensive therapy. That's how you interpret this, right? So absolute risk difference is something that we don't use very frequently. So why should we know it? Because a reciprocal of that is called numbers to treat. Let's do this example, right? So 1 divided by reciprocal of 0.15 is 1 upon 0.15. That's 6.6. The interpretation is treat at least 6.6 is about 7. So treat at least 7 to see an effect in 1, right? So if you treat 7 people intensively with diabetes, you will prevent PDR in 1. That's basically the take home message here compared to treating with conventional, right? So let's take an ophthalmic example, clean slate. Let's look at endophthalmitis with an example, and you will perhaps need to do these calculations. So say you are giving intracameral moxifloxacin, and there are 60 out of 5,000 patients in this who got endophthalmitis. That's the event. So what is the risk of endophthalmitis? 60 divided by 5,000, right? And no intracameral moxifloxacin was given in 5,000. Out of that, 125 got endophthalmitis, right? So what is the risk difference? 60 divided by 5,000 minus 125 divided by 5,000, right? That is 0.012 minus 0.025 if you're doing the math with me. So when you subtract this, you will get 0.013, right? Let me quickly do it so that I am also not making a mistake, and if you are doing it with me. So 0.012 minus 0.025, right? That's 0.013. 0.012 minus 0.025. Now let's reciprocal that. 1, now forget the minus sign, just reciprocal that. 1 divided by 0.013. You will see the answer is about 76.9. That's 77, right? So 77 means if you treat 77 with intracameral moxifloxacin, you will prevent 1 endophthalmitis. Isn't that's good enough, right? So I would now want to treat based on this, because endophthalmitis is something which is something where we want to even if I prevent 1 injection by giving 1,000 injection, I'll still be okay with it, right? So that's basically how so this is numbers needed to treat in NT, or numbers needed to treat. So you can do this calculation for pretty much anything where you have a experimental and a control group, and you have these event and no event, right? So do I want to do MIGS for this kind of patient? And so you will say, if I do 70 mgs, I'll prevent progression in glaucoma in say 1. But then if I do trabeculectomy, my numbers are better compared to no treatment, say. So then I still don't want to do mgs because my success is slightly better than trabeculectomy. But then there are so many other examples. So especially rare events, say like globe perforations with blocks, so peribulbar versus retrobulbar. You will see that if you give say 300 peribulbars, you will prevent one this thing perforation, right? So that's pretty good, isn't it? So numbers needed to treat will tell you how much you want to adopt something in your own practice, given the benefits of that versus the risks. Now let's look at risk ratio. We are going into more complex things. It's not complex again. So this is just A upon A plus B divided by C upon C plus B. It's a ratio. It's a division. So A upon A plus B, when you subtract it, you get risk reduction, right? Absolute risk difference. When you just divide this, you will get a ratio. This is called a risk ratio. So again, this is basically 0.06 divided by 0.21. It's not subtract. 0 divide by that. So that's 0.29. Now 0.29 really is 71% lower risk of progression. So when we look at how to do this, but it's 1 minus 0.29. So it's 71% lower risk of progression on intensive therapy compared to conventional therapy. So this is risk ratio. Odds ratio means the odds of the event happening versus not happening. So here you are not looking at the total exposed. You are looking at A divided by B and that divide C divided by D. So A upon B divided by C upon D. You're not looking at the total numbers. You're looking at the odds of the event happening versus not happening, not out of the total. This is the difference between risk ratio and odds ratio, right? So A upon B divided by C upon D, right? So this is odds ratio. So here you will see that's pretty similar to the risk ratio. I hope you are with me because it's not really that difficult, right? So as you will see, the events which are relatively rare will have very similar risk and odds ratios, but the events which are more common, this no progressions or this no event will become smaller and smaller. They will be relatively closer to each other, right? So so the risk in the exposed versus non-exposed becomes different. So if it's a rare event, risk ratio and odds ratio is relatively similar, right? So odds means odds of the event happening. So how do you interpret this? If the risk or odds ratio is 1, that means there is no increase or decrease in that risk or event happening. So there is no association between the intervention and the outcome. If it is more than 1, there is a positive association, right? So if that risk increases, the odds of the event increases. If the risk decreases, the odds of the risk event decreases. And if it's less than 1, then it's a negative association. So if one increases, the other decreases. It's not in the same direction. It's a negative association, right? So if you give more and more intensive therapy, the risk becomes lesser and lesser of PDR happening, which is understandable, right? So a negative association, that's how we do it. When you're looking at continuous outcomes, that's even easier. Say let's look at Gingo and Bilboa extract versus control groups for say management of AMD, and you say 2.3 line improvement in BCVA in the Gingo and Bilboa group versus 0.6 mean improvement. This is a mean response now. Remember, this is a continuous variable, right? So what we then say is so you just basically subtract the two. 2.3 minus 0.6 is 1.7. So the difference in average visual acuity of 0.17 units or logmar units indicates better response in the Gingo group. It's not at all, it's relatively simple, right? So now what is 95% confidence interval is, so if you say, say the risk is, say the odds is, whatever 2 times or 1 time, 1.5 times, is it going to be the same all the time? If you say conduct the experiment 100 times, you will get some variability, isn't it? So that's what the confidence interval says, where you will say this drug is better than drug A is better than drug B and 2.3 times better than drug B, but it could be 2.1 times better and 2.8 times better. So there is a range, and that's what we talk about when we talk about confidence intervals. Let me go beyond this. So these are some of the things which I have written on my website as well. So there is something on p values, and then p value really means the same thing. So if you repeat a study 100 times over, how many times are you likely to get the same result versus how many times are you likely to get a different result by chance, right? So the p value of 0.05 means you will get a different result 5 out of 100 times, but 95% of the times you will get the same result. That's how you interpret p values. Let's quickly look at how do you review RCTs, and they're slightly different because of assessment of bias. So selection bias, like I said, it's overcome using randomization. This is I think something that we've already seen, right? The physician can't tell where you should go. It has to be either a toss of a coin or a roll of a die or something like that. So randomization takes care of selection bias only. Other types of bias like information bias is taken care using something called masking, and I'm sure all of these things. Something called attrition bias. Attrition bias means loss to follow up. So you're doing a randomized trial, and you had 50 patients in each group, but only 35 turned up in each group. So there are 15, that is 30% loss in each group. Now what do? Do you go and randomize more people? But then, by what happened to them who are already randomized, right? So when they may not come at one visit, but then they turn up in another visit. So do you drop them totally or do you keep them? So remember the dictum, once randomized, always analyzed, right? So what we do is, say there is missing data right now because the patient did not come, say in one of the between visits or maybe even the last couple of visits, you generate data. that is called generating missing data, and there are many ways to do it. Commonest way is called imputations, and this is getting more complex, and I don't want to go into the details. Now, this entire thing of analyzing after generating missing data is called ITT, or intention to treat. Okay, so you might have read about this terminology in a lot of published papers. So that is what we mean by intention to treat. Almost every trial, when there is loss of follow-up, will use this intention to treat. And God alone knows how they are actually generating that missing data. And most large trials will do it in the right way. But that's what is intention to treat. So these are all the ways of overcoming bias. And remember, confounders are also there. So, how do you, so they may be associated with treatment as well as the effect. Say, for example, endothelial count in phaco versus SICS is what you're trying to study, right? Age is a confounder, right? So, overall, you may say, oh, the endothelial count is lower in SICS versus phaco. Or phaco endothelial counts are better than SICS. So, phaco you should do in not SICS. But that blanket statement is not okay, because SICS patients may be much older with much denser cataracts, where you don't want to actually do phaco, right? So if you have randomized, it's a different question, but otherwise, age is a confounder, density of cataract is definitely a confounder, maybe pupil size is a confounder, right? So we'll do phaco in younger patients with thinner, with sort of softer cataracts with well dilated pupils, and SICS in much tougher cataracts with much older patients with more smaller pupils. So those patients are already going to have lower counts in itself, isn't it? So age is a big confounder there. So also, so at baseline, are they the same, and all that you need to see. Say CME post phaco versus SICS, diabetes is a big confounder. So if you have a lot of patients in the SICS group who are diabetics, then that SICS may have more CME post-op, and then you will say, oh, phaco is better than SICS. Why? Because SICS is causing more CMEs. But then diabetes was something that you did not adjust it for, right? So the real question is, what if both the groups have the same number of diabetics? Does SICS still cause more CME than phaco? That is how you do it. So confounders are adjusted using all these odds ratios, risk ratios, and all that we talked about. Systematic reviews are a slightly different, I don't think we have enough time to get into the details, but remember, the methodology here is more important than the results, right? So how was the data extracted from, systematic review means it really should be systematic. And remember, the commonest way of writing a review is a narrative review. Narrative review means, मुझे क्या लगता है, I just put it down on paper. And systematic review means we systematically go through the whole literature of 1,000, 1,500 papers, and then select some that are important to our study question, and then write that review, right? So there has to be a protocol, a search strategy, data extraction, and all of these things. And meta-analysis has many different things which we may not have time, but then you should see something like this this is called risk of bias assessment, right? So this is analysis of a paper which is taken, files which are taken from a meta-analysis, right? So you should see some figures like this, which talks about assessment of bias. And meta-analysis also should have something called the forest plot. Again, like I said, we don't have a lot of time to get in the details, but so meta-analysis and reviewing, that is slightly different. So if you haven't done any or don't know much about meta-analysis or systematic reviews, then please decline reviewing those, because a poorly reviewed meta-analysis does lot more harm than actually a poorly reviewed case report. So meta-analysis should be left to the experts to actually review. Lastly, about causality association, consider the following bias before establishing causality. So bias of biological gradient or treatment effect, biological plausibility. So let's take an example to understand this. So COVID-19 and retinal vein occlusion was a huge, everybody said, oh, if you have COVID-19, your risk of retinal vein occlusion increases. Why? Because it's prothrombotic. So there is a biological plausibility, right? And then, oh, you have COVID-19, tumko to RVO ho hi gaya. And it's almost like that, people started talking in those terminologies. However, when very large databases were looked at, people with RVO had a lot more diabetes, lot more hypertension, and a lot of these other comorbidities. Right? And therefore they got it, not because of COVID-19. So COVID-19 causing RVO is a no-go, but the brain makes it very, it's very easy for us to associate. So there is no causality there, but then we establish causality without going into all of this. So is there bias in this biological gradient? Is there biological plausibility? Are there other causal relationships, right? Like I told you, and is there experimental evidence actually? When somebody has actually done a big study, and when that experimental evidence was produced, they found from large US databases that COVID-19 or no, RVO risk has not increased. COVID-19 vaccine causes optic neuritis is another one. HCQ and heart disease. I showed you that paper which was finally retracted, isn't it? So there is not much in this. So causality, saying that A came before B. So ये हुआ इसलिए तुमको वो हो गया. So you blinked, you sneezed twice, therefore you got a PC rent. Is perhaps not true, isn't it? I mean, though we would like to blame it on the patient's sneezing, but then maybe you look at ourselves and see, oh, something problematic that I did, because of which patient got a PC rent. So causality is something which we should be very careful about, especially when we are reviewing papers. Not not otherwise, but I mean, of course, otherwise too. But when we are reviewing papers, that's very, very essential. If you endorse that causality, it could become gospel later on. So then, be very responsible and try to really see if there is causality. Right? So this is something that I thought we'll take a look at pretty quickly on how to define the study question using the PICO approach. Is the study design appropriate to answer that study question? Is the statistics done well, where you look at odds ratios, risk ratios, numbers needed to treat, and all of those. So most good papers will have those metrics. And reviewing randomized trials is slightly different, as I've shown you, where you look at randomization, masking, and intention to treat and all of that was done or not. And systematic review is again different from reviewing routine papers. Lastly, before going, this is a screenshot from the Equator Network. This is a website which has these checklists. So these are reporting guidelines for study types. So you may have heard about this. So randomized trials should be written using the CONSORT checklist. The CONSORT is a word which a lot of people have heard. Observational studies should be written using the STROBE checklist. There are 21 questions which you should use to write that paper. Systematic reviews that I was talking about should be written using the PRISMA checklist. Let me just go back and show you that one here. So the quantitative methods written with the PRISMA or the Moose checklist, right? So so checklists need not be used only for writing, but can also be used for reviewing papers. It may not be very helpful, and all of these other questions that I showed you are perhaps more important and applicable generally. But if you are reviewing an RCT, makes sense to look at the CONSORT. You will find that maybe in all of that information, when you come to review an RCT, you will find that out of all of those information given, point number 11A, which talks about masking, is not there in the paper. You read that question and then you see, iska answer kya hai bhai paper mein? And you will say, oh, there is nothing there. Oops. Then you will perhaps say point 16, which is important, is not there here, which is like the limitations of the paper. That RCT is written very well, but it doesn't talk about its own limitations. So you point it out. So you can use checklists to review papers as well. Say case report you are reviewing, you can use of course writing, you use the CARE checklist. If you are reviewing also, you can use the CARE checklist, right? So this is another way of reviewing papers. We may not have time for live examples, and you can tell me if you want to do that. But so overall, there's something called peer review week, which happens once. It's in the last week of September every year, and there are themes every year for peer review. So it talks about ethics in peer review, and then it talks about process in peer review. So it makes sense for reviewers as well as editors to have your eye out on the peer review week and attend a lot of webinars and excellent talks which happen during the peer review week. There's another website called the ASAP Bio, which is revolutionizing the way we look at preprints, and they also have a lot of sessions during peer review week, and they talk about peer reviewing preprints, where it is not yet published and it's just there on a website, but then you can actually review it, and it's subtly different from actually reviewing for a journal. So ASAP Bio is something that you can actually look at and sign up for its newsletters. This is my website. I think a lot of you would have seen it. It's Sengupta Research Academy, and I look quite different from how I used to look when the website was made. It has a lot of learning material on how to do research, and so there is a section like lecture on what a reviewer wants, and I have actually talked far more in detail about it. But then a lot of sections on how to write a paper, how to do a good literature review, and the sort of the blockbuster really is the statistics module, which talks about how do you make an Excel, and how do you do some statistics on your own, and how do you communicate with a statistician, right? And some advanced biostatistics like like regressions and all these odds ratios, which I have briefly glanced upon as for you to know as a reviewer. And there is an online fellowship, and you can explore the website with a lot of good material to read, about 30 blogs and talks about varied aspects of different aspects of clinical research, like sample size, thesis to journal articles, and all of this. And you can also sign up to the newsletters, where you will get a lot more information about writing. So I'm happy to take questions now, and if you want, I can actually show you quickly about a live demo on reviewing papers if you have the penchant for it. But then if not, then I'm happy to stop here.
That was really a wonderful interaction about the peer review paper. Rahul,